In this tutorial, I'm going to introduce the idea of a two-way ANOVA or factorial analysis. This video is part of a playlist, and in the playlist I describe all the different aspects of a two-way ANOVA, from calculating it by hand to interpreting results, SPSS, and also Microsoft Excel. And you can find a link to the playlist below right there. Let's imagine I give an arithmetic test to boys and girls of different age groups. 10-year-olds, 11-year-olds, and 12-year-olds. And now I have a list of test scores, and I want to determine what impacts the variation. Is it gender, is it age group, or is it both gender and age group? So I have two factors. I have gender and age, and that's why it's called a two-way ANOVA or factorial analysis. I have two factors. If I was going to analyze this same data with a one-way ANOVA, and let's say I just looked at test scores variation by age, so I have 10-year-old group, I have my 11-year-old group, and also I have my 12-year-old group. I would take the average of the 10-year-old group, their average test scores, and the average of the 11-year-old group, and also the average of the 12-year-old group. And I'd compare these back and forth, of course. I'd also look at the group as one big large group, and I would take the sum average or the total average of the entire group, which is equal to 9, by the way. And in the end, I would take all these averages and I'd build a little table of just averages. Let me organize this. Let me move this around a little bit. So I end up with one row and it's all averages. In the end, I just have a row of data, all averages by age. Now in a two-way ANOVA, it's different. It's more complicated. So let's imagine I want to analyze my data by age and gender. So I'll put everything back, and let me put my test scores back in for the 10-year-olds, 11-year-olds, and 12-year-olds. Now I have everything the way I like it. So I have above the first group of data, I'm going to label as boys, and the bottom group is girls. I take the average data or average scores for each age group for the boys. Then I take the total average for all boys, which is 7.7. Now I do the same exact thing for the girls. I take the average for each age group, and then the total average for all the girls. And their average score is 10.3. Now let me put this all back into a single table. I'm going to call that the mean table. And I'm going to end up with three rows of data, boys, girls, and the average row. And I'll also have 4 columns of data, the 10-year-old data, the 11-year-old data, 12-year-old data, and also the average there. In this table, I end up with averages for all the boys by age group and total, also averages for all the girls by age group and total. I have 10-year-old data broken down by gender and total average, 11-year-old data broken down, and 12-year-old data broken down. Having data organized in a table like this makes it easier to calculate degrees of freedom, to understand the factors, and also to make any of the other calculations I have to make. My first factor is, I'm going to call that gender. First factor is my gender. My second factor is age. And it doesn't make a difference what I call my first factor or my second factor. I could swap those if I wanted to. A two-way ANOVA is a lot more complicated than a one-way ANOVA. In fact, if I put that one-way ANOVA table back in, you'll see that the average for the two-way is the entire table for the one-way ANOVA. In a one-way ANOVA, I'm going to work with 4 different averages, and in a two-way ANOVA, I'm going to have 12 averages. Having data organized into this nice table makes it a lot easier to work with and a lot easier to understand. In essence, what we're doing with a two-way ANOVA is we're taking our data and I'm going to reorganize it in a variety of different ways and analyze it. I'm going to organize it based upon age group. And I would calculate sum of squares of my first factor, which is age. Then I'll reorganize the data, and this time I'll organize it by gender. And this time I have a thing called sum of squares factor again, but of gender. This is my second factor. So I'm going to analyze it based upon gender. And finally, I'm going to take all the data and treat it as one big chunk. And this is called my total sum of squares, or sum of squares of the total. And I'll take the mean and I'll analyze it this way as well. In the end, I have sum of squares of the first factor, which is gender, sum of squares of the second factor, which is age, sum of squares of both factors, age and gender interaction, sum of squares within the error. And if I add all these up, I get sum of squares of the total, or total sum of squares, both the same thing. In the next video, I'm going to show you how to make all these calculations by hand. In subsequent videos, I'm going to show you how to calculate the F ratio and also how to calculate degrees of freedom. I'm also going to show you how to interpret the results, how to come up with a rejection region. If the F ratio is in the red area, we reject the null hypothesis. If it's in the green area, we fail to reject the null hypothesis. The first hypothesis we're going to test is gender will have no significant effect on student score. The second hypothesis is age will have no significant effect on student score. The final hypothesis is gender and age interaction will have no significant effect on student score. So up next, I'm going to show you how to make a lot of calculations by hand if you must. And again, the playlist is right below. I'd recommend you go through the videos using the playlist. As always, share the knowledge, share the love, Facebook, Google+, Twitter. Comments, questions, links below. Don't forget to subscribe.